Okay, so this next video is going to look at logarithmic functions. So just one quick addition to the exponential functions. The textbook does have a very nice explanation about compound interest and setting these problems up. So I would read through that section in the textbook as well if you're having a little difficulty thinking about these problems a little bit. So logarithmic functions are the inverse of exponential functions. What that means is if you have, like for example, a function that's y equals 2 to the x, its inverse is y equals log base 2 to the x. And that means that if I compose these two functions, if I do 2 raised to log base 2 of x, or if I did log base 2 of 2 to the x, both of those would just equal x. They reverse each other's properties. It also means graphically they are reflections across the y equals x line. So the log function with base a. Wow, okay, my cat is trying to mimic some birds again. Interesting. So we have a function log base a of x, and that's going to be where a is greater than 0 and not 1, and x also is greater than 0. And then this is only true if and only if x is a to the y. That's the definition of the log function. So if this is basically coming out of that inverse property. The natural log function, so when the base is when the base is e, and so f of x equals log base e of x, this is written as ln x as a natural log. So we read this as natural log of x. We have some basic properties of logs. There's a lot more properties that we'll look at in the next section, but the basic properties that just come out of the definition are that log base a of 1 has to be 0 because a to the 0 is 1. Log base a of a has to be 1 because a to the 1 is a. Log base a of a to the x is x, and a to the log base a of x is also x because of the inverse property. And if log base a of x is log base a of y, then x has to equal y. This is the one-to-one property. For things to have inverses, they have to be one-to-one functions. And so we know that if you take the log of some number and it equals the log of a different number, then those numbers have to be the same number. Again, those are all in your textbook as well. We can look at the graphs of these functions. So a log function looks like this. So it's basically if we take the exponential function, look like that, and then flip it around the line y equals x, we'll get this function. The domain of the log function is going to look like the range of the exponential function. Remember, these are inverse functions, so the domain and range basically get flipped. So the domain of a log function is 0 to infinity, whereas the range is all real numbers. And remember, in exponential functions, the domain was all real numbers, the range was 0 to infinity. This one doesn't have an y-intercept, but it has an x-intercept at 1, 0. It's always increasing from 0 to infinity. It does have an asymptote. In this case, it has a vertical asymptote at x equals 0, just like how the exponential function had a horizontal asymptote at y equals 0. And it's continuous on its domain of 0 to infinity. Again, same with exponential functions. I don't think I mentioned it before, but review your transformation. So you should know your a, h, and k values. Right, so like shifting things up and down, translations, stretching and shrinking, reflecting, you should be able to do all of that stuff. If you aren't sure how to do it, you should go back through your notes for the earlier sections and look through that, or try to just go through it on your own. There's some problems in the textbook as well that you can use to help you with that. So we'll do an example modeling problem with logarithmic functions. So log functions are also used very frequently to, especially when scaling is an issue. So if you have things that are have huge spaces between each value that you need, it's easy to think about them in a log scale. Basically, you're thinking of them as powers rather than as straight up numbers. For example, a lot of times logs get used in pH, right? So it's the concentration of hydrogen ions. And you have a lot of hydrogen ions in different solutions, but supposing you have a difference of like 10 ions versus 10,000 ions, instead of thinking about this difference as like 9,990, which then makes your scale just really, really big and it's really hard to classify, we can break this down into powers of 10, where we can say like this is 10 to the 1, this is 10 squared, 10 cubed, and 10 to the 4. So on a log scale, this would just be 1, 2, 3, and 4. And so then here we only have differences of 1. It kind of looks linear rather than exponential. And that helps us more just with dealing with things more easily. We like dealing with lines more. It's easier to solve. It's easier to use. Just knowing that now we're doing it on a log scale instead. Later on in this chapter, we'll do an example of where we actually do this modeling step, where we look at something exponential but then change it to a log scale and then think about it more as a line rather than an exponential. So this model is a memory model. It's how much material people retain after every month from learning something. And they came up with an equation for it. Basically, they gave a student some tests and they looked at the score on the test over time. So the first question is, what is the score on the original exam? What's the average score? So the original exam, that would be t equals 0. So we can do f of 0. That would give us 75. That's like our initial value as well. At the end of 3 months, then we'll do f of 3. And you would type that in your calculator, get that number. And then at the end of the year, well, that would be after 12 months. So you do 75 minus 6 ln, 12 plus 1, and you type that in your calculator and check the value. So mostly for the log models, you'll be given a model and you'll just have to use it. But we will go over in a later section how to create a log model for certain situations yourself. And so stay tuned for that. That will probably be next week. Well, not next week because that's spring break. The week after.